Hello everyone, so let's continue on with looking at disturbances to chemical equilibria. And in this example it says we look at carbonyl bromide, which decomposes to carbon monoxide and bromine, and we're given the chemical equilibrium. It says Kc is 0.19 at 73 degrees Celsius. Suppose you place 0.5 mole of carbonyl bromide in a 2 liter flask and heat it to 73 degrees Celsius. After equilibrium has been achieved, you add an additional 2 mole of carbon of the carbonyl or carbon monoxide. How is the equilibrium mixture affected by adding more carbon monoxide? So that is our first question. So it's a qualitative discussion. And thinking about that, it's basically carbon monoxide is a product. So if something is already reached equilibrium and then you add a product to it, in principle all that should happen is you've increased a product concentration. The Chatelier's principle says that the system will react to oppose the disturbance, and hence it would want to decrease that concentration. So in other words, the system would want to reduce the carbonyl concentration, or the carbon monoxide concentration, and hence it will reduce the product concentrations, favoring the reverse reaction, increasing the concentration of the carbonyl bromide, shifting the equilibrium to the left. So we can write it in some manner, but essentially the resultant what will happen is that yes, the system will shift to the left. So let's write system, or let's write equilibrium. Left, right? And you can also see that from Q. If you wanted to go and calculate Q, or think about Q in terms of what will happen there, I think it's a good exercise for you to think how can Q help you also predict that the system or the equilibrium will shift to the left. Alright, let's move on to B. So it says B, when equilibrium is re-established, what are the new equilibrium concentrations of the carbonyl bromide, the carbon monoxide, and the bromine? So this is a bit of a longer question than it might initially appear, because it says, if you read the question fully, it says, suppose you place 0.5 mole of carbonyl bromide in a 2 liter flask and then heat it to 73 degrees Celsius. After equilibrium has been achieved, you add an additional 2 mole of carbon monoxide. So that means we had an initial situation where we placed a certain amount of carbonyl bromide and let it decompose. Then an equilibrium was reached. So meaning there would be equilibrium concentrations which we need to calculate. We need to figure out what those are. Once we know what those are, then there was a disturbance, and the disturbance to that equilibrium was placing 2 mole of carbon monoxide in the flask. And then there is a new equilibrium which we can calculate from that point. So in other words, and then we must calculate those new equilibrium concentrations after the disturbance. So we're going to do a double ice table to calculate everything. And our starting point is to first, of course, calculate what was the initial concentration of the carbonyl bromide. So let's go ahead and do that. The carbonyl bromide, initial concentration, 0.500 mole. So number of mole divided by the volume, which is 2.00 liter, gives me 0.25 molar. Okay, so now we can go ahead and do our first ice table. So our initial concentrations, we only have carbonyl bromide. We didn't have any carbon monoxide or bromine. So that's that. To know the change or the direction of the change, let's calculate Q. Always just good to keep in the habit of that. So Q in this case is equal to carbon monoxide multiplied by bromine divided by carbonyl bromide. Alright, and we see, well, that is equal to 0, 0 divided by 0.25. So that means it's 0, which is of course less than the Kc, which is equal to 0.190. So that means our forward reaction is favored. Alright, so that informs our decisions here. If the forward reaction is favored, it means our reactant must decrease by X and our products must increase by X. There's no different stoichiometry to take into consideration here. So all of them are 1 to 1 to 1, so there's just minus X and plus X. So therefore at equilibrium, 0.25 minus X, X and X. Okay. So then to calculate what this X is, we can say Kc, which is equal to 0.190, is equal to the equilibrium concentration of carbon monoxide multiplied by the equilibrium concentration of bromine divided by the equilibrium concentration of COBr2. And these we get from the ice table, of course, right? So that's X, X, and 0.25 minus X. We can check if we can do approximation, but you should see that Kc multiplied by 100 is 19, and that is larger than our initial concentration for carbonyl bromide. So we can't do an approximation. So the best that we can do here is we can start to simplify. So that becomes X, 0.25 minus X. And if I expand this, then eventually I get to the quadratic expression of X squared plus 0.190X minus 0.0475 equals 0. We can then use the quadratic expression or quadratic solutions for X, so minus B plus minus square root B squared minus 4AC over 2A to get the roots here of X. So of course A, B and C, and the values that I got here for X, X1 is equal to minus 0.3327 and X2 was 0.1427. Each of these are molar, and the negative value is impossible. Right? Why? Because, well, we can't have a negative equilibrium concentration. So if you link it back here, you can't have a negative concentration. Right? So that means only X2 is a viable option for us to utilize going forward. So that means at equilibrium, our concentrations are for COBr2. At equilibrium, it's 0.25 minus X. And remember, you don't round here because it's not the final answer here. So it's 0.10725, a bunch of numbers, molar. And for the carbon monoxide and the same. They're both equal to X. So they're equal to the 0.1427 molar. Okay. Right, so that's our equilibrium. So it says so that's our equilibrium. After equilibrium has been achieved, you add an additional 2 mole of carbon monoxide. So it says that's what happens there. So that's the disturbance. So when equilibrium is re-established, what are the new equilibrium concentrations? So that's what we're after. So technically, we then do another ice table with these as our initial concentrations. So this one is 0.107 25 molar. The carbon monoxide, we need to remember that its initial concentration is going to be 0.1427. We don't have to put the molar, 27. But what did we do? We had a disturbance, right? So we need to add an additional concentration to it. So how much carbon monoxide did we add? We said 2 mole of it. So 2 mole in a 2-liter flask. So what is the carbon monoxide, let's say, added? It's equal to the 2.00 mole divided by 2.00 liter. And that should give you a value of 1.00 molar. So that means the initial amount of carbon monoxide then is its value at equilibrium plus a value of 1. All right. So that's what it gets. The rest didn't have a disturbance. And the bromine, well, it is just at what it was at equilibrium. So 1.427 and so on and so forth. If you want to split this up into a couple of steps, so meaning values at equilibrium, disturbance, right? What is the disturbance? Plus 1. Initial values, you can split it up into multiple steps. You can put them into one table. I'm just showing different variations that you can use as long as it's some sort of logical thing that you illustrate. All right. Now that we know how much it is, so I've now shown that. So let's just write it as its initial amount. So it's going to be 1.1427. Right? I've just added the 1. So now we know how much we have initially before the new equilibrium is re-established. The question now is, in what direction does the new equilibrium establish itself? So hence again, we need to test the Q. So Q is equal to CO BR2 divided by CO BR2, and we use these new initial concentrations, 1.4, sorry, that's where the 1 goes, 1.1427 with 0.1427, and the COBR2 is 0.10725, and I got here a value of 1.52, etc. And if we compare that to KC, KC is 0.19. We see that that is indeed larger than KC, equal to 0.19. All right, so in this case, Q is larger than K, so that means the reverse reaction is favored. Okay, so that infers what we must do here. If the reverse reaction is favored, it means our products need to reduce in concentration, and our reactant needs to increase in concentration. All right. And again, the stoichiometry is 1 to 1 to 1, so it's always 1x in this case. So at equilibrium, we have 0.10725, keep all the numbers, plus x, 1.1427, keep all the numbers, minus x, and 0.1427, keeping all the numbers, minus x. All right. And now, just as we did here at the top, we use Kc to solve for x. Kc, remember, Kc doesn't change unless the temperature changes, so Kc remains the same. So we just plug it in, 1.14, so it remains that same expression we had there. So 1.1427 minus x multiplied by 0.1427 minus x all divided by 0.10725 plus x. And I mean, you can go do the maths. You're going to get another quadratic expression, and you're going to solve it using the quadratic formula. And I really wish you good luck with that. And hopefully you get to the point where you solve, and one of your roots is going to be 0.10408 and a bunch of numbers molar. Okay, so plugging that back in to our table, we should get COBr2 at equilibrium equals to 0.10725 plus x being that. So that means rounded, we can actually now round because this is the final answer, gives us 0.211 molar, 3 significant figures. The concentration for carbon monoxide at equilibrium is equal to 1.1427 minus x. So that gave me 1.04 molar, and the concentration of bromine at equilibrium was equal to 0.1427 and some numbers minus x, and rounded, that was equal to 0.0387 molar. Okay. So a lot of work, but in principle the same application of the same ideas over and over again. All right. So that's what happens to B. All right, and then finally C. Does adding carbon monoxide affect the percentage decomposition of the carbonyl bromide? Short answer, yes. I mean, it does affect the percentage decomposition because the equilibrium shifts to the left, right? So do you notice what is the differences between the values of carbonyl bromide in the first equilibrium and after adding carbon monoxide? Our amount of carbonyl bromide has increased. It's almost doubled. It went from 0.1 to 0.2. And hence, that means that the amount, if we compare that to the amount that we initially started with, so the percentage decomposition here, so let's make a note of that. So the percentage decomp here is roughly about 50%, right? Because what's that? 0.1 divided by 0.25, it's actually probably about 40%. So meaning the amount that has reacted, the amount that has decomposed is, not 40%, 60%. It's the amount that has reacted. The amount of carbonyl bromide that has reacted in this reaction is about 60%. But by adding the CO, we see that, well, now there is 0.211 left of it. And that means that there's only 0.04 of it that actually reacted. And that means it's less than a fifth. So it means that the percentage decomposition here, percentage of decomp in this case, is only about 20%. So it means the decomposition percentage has reduced from 60 to almost 20% by adding the carbon monoxide. So yes, adding carbon monoxide affected the percentage decomposition of the carbonyl bromide, and it makes sense that it does, because it should have shifted the equilibrium to the left, because adding carbon monoxide is a product. It shifts the equilibrium to the left as per the Chatelier's principle, and hence increases the amount of carbonyl bromide, meaning what's the anti of decomposition? It reforms the carbonyl bromide. All right, so that's just a question to make you think about the effect again of the carbon monoxide. All right, so long question, but in principle just the same mechanics over and over again. Cool. Thank you for watching, and I'll see you in the next one.